Today we're going to get started on lab number 9, multivibrators. Basically we've been talking about clock signals. So referring back to last week's lab, figure 9.6 has a waveform diagram for a clocked RS flip-flop. And you can see we've got outputs for Q and our inputs for R and S, and we have an input for a clock signal. And a clock signal is just a repetitive signal that gives us ones and zeros and ones and zeros and just keeps repeating the pattern on and on. So in today's lab we're going to start generating clock signals. We have a few new items that we need to cover. We're going to be using a 7414 Schmitt inverter, and it looks like a regular inverter, but you'll notice it has this little hysteresis symbol in here, so we need to cover that. We're also going to be using some capacitors, so we need to talk about the capacitors that we're going to be using. We're going to be using a few different resistors, so I've given you the color codes for each of the resistors that we're going to be using. We're also going to be using several capacitors. Your capacitors in your kit are either going to be of a ceramic disc type or they're going to be of an electrolytic type. So I have an assortment of capacitors here. These are all under 1 microfarad in size. You can see our standard ceramic disc here. It's labeled 473, so that would be 47 nanofarads. I have one here labeled 10N, so it would be 10 nanofarads. You can see I've got one here and it's got 6 different colored dots on it. So that would be a code that you'd have to look up. I have some that have colored bands. So this one looks like it's brown, black, orange, white. So you'd have to look those up. This is an interesting one over here. It seems to have 3 color bands. It looks like it's kind of a gray, red, red. Not sure what that value would be. I have some that come in square boxes. Some that come with axial leads, some that are really small. So I just wanted to give you an idea that capacitors come in many different packages, many different sizes. You can see that this big one here, it's got the numbering on it 680K400. That means this guy is good for 400 volts. If they're of the electrolytic type, there is a positive and negative lead, and on your schematic symbol you can see that there is a plus sign. On your capacitor itself, one side will be labeled negative, so that's the negative side. The shorter lead is the negative, the longer lead is the positive. Capacitors can be confusing. Here I have 4 capacitors. While they physically look different, they're actually all the same value. I believe this is the capacitor that came in your kit. You'll notice it is labeled 100 microfarads. It does have the minus sign down the side. It has a long lead and a short lead, and it's good for 50 volts. This larger blue capacitor has a negative sign down one side. You'll notice one leg is longer than the other. The can is labeled 100 microfarads, but it's good for 63 volts. The next capacitor I want to show you is this black one. It's 100 microfarads, but it's only good for 25 volts. And it has the negative sign down one side. And it has a long leg, which is the positive leg, and a short leg, which is the negative leg. On this last capacitor, it's blue. It has the negative sign down one side. It's 100 microfarads, and it's good for 25 volts. So while each of these capacitors looks a little bit different, they're still all 100 microfarads. The size of the can represents the amount of voltage it can handle, but we don't need to worry because we're only using 5 volts. I wanted to show you these two capacitors. This one is 33 microfarads, and it has the line down one side, indicating that's the negative side. It has the long lead and the short lead to tell you which way around to put the capacitor in. This is considered a radial axial capacitor. It's radial like the radial engines in the old biplanes. And if you look at this capacitor, you can see that leads come out of either end of it. There's a little line that goes around it that indicates the negative end, and there's a dent in the can to indicate the positive end. This is considered an axial lead capacitor, like the axle in your car. So when you're looking at an electrolytic capacitor, it's very important that you get the positive and the negative leads in the right way around. The long leg is the positive lead. If you use this capacitor backwards, then they can explode. And you notice this one on the diagram is good for 25 volts. If you were to try and put 100 volts on it, it would also explode. So these can be very dangerous. So capacitors that are 1 microfarad or greater are usually labeled in microfarads. So you can see this particular capacitor is labeled as 100 microfarads. This is approximately the size of the capacitor you'll get in your kit. You can see that it is fairly small, and it is labeled 103. So small capacitors of 1 microfarad or less are usually labeled in picofarads. So you'll notice yours was labeled 103. 103 represents digit, digit, and a multiplier. So you can see the first digit was 1, the second digit was 0, and the multiplier was 10 to the 3. So that's 10,000 picofarads, or 10 nanofarads, or 0.01 microfarads. So we're going to reference Schaum's Basic Electricity 2nd edition textbook. So we're going to reference the textbook to understand what's going on with capacitors. So if you take a little look at figure 1-4, it says forces between charges. So it shows you here that like charges repel. So these are two negative charges repelling each other. Here we see two positive charges repelling each other. And over here we can see that a positive and negative charge, unlike charges, attract each other. And in chapter 14 they talk about a capacitor, and it says a capacitor is an electrical device which consists of two conducting plates of metal separated by an insulating material called a dielectric. So here we have an example. We have two conducting plates separated by some kind of dielectric. We have the symbol for a fixed capacitor, and you can see this would be a non-polarized and this would be a polarized capacitor. We can also have variable capacitors. So on page 306 we have a nice definition for capacitance. It says electrically, capacitance is the ability to store electric charge. Capacitance is equal to the amount of charge that can be stored in a capacitor divided by the voltage applied across the plates. And table 14.1 tells us the type of capacitors. We can have air capacitors, so there can be air between the plates. Our smaller capacitors are going to be the ceramic capacitors, and they usually come in a disc. And we're going to be using the electrolytic capacitors, usually constructed of aluminum. So I found this little definition on the internet. It's about capacitors and DC circuits, and it says a capacitor is a gap in a circuit with space for charge on the plates as shown as horizontal lines. So this is a plate and this would be another plate. So when a capacitor is charged, electrons on the lower plate repel electrons from the upper plate, which then move to the positive terminal of the supply. So we can see here that we have an initially uncharged capacitor with the same amount of positive and negative charge on each plate. Then when we charge a capacitor up, we can see the negative charge on the lower plate repels electrons from the upper plate, leaving a positive charge. So this would be an example of a charged capacitor. I also found this graphic out on the internet. It gives an example of a 102K. Now, the K is actually a tolerance band. So when we look at tolerance code tables, we can see that a K would be plus or minus 10%. The tolerance on capacitors can go all the way down to Z, which is plus 80% minus 20%. So you can see it's harder to make a capacitor to the correct value than it is to make a resistor to the correct value. The first circuit that we're going to wire up is going to be using the 7414 Schmitt inverter gate. So this is the 7414. You'll notice it looks very similar to a standard inverter, except it has this little hysteresis symbol on each of the logic gates. So hopefully you'll remember back to figure 6.1 when we first started logic gates, and we said that for an input voltage we had to have 0 to 0.8 volts for a logic 0 and 2 to 5 volts for a logic 1. On a Schmitt trigger, what happens is once one of these levels is triggered, the other level will not be triggered until we get down to the next level. So if we input a logic 1, it would remain at a logic 1 until our signal got down below 0.8 volts. Then it would remain at a logic 0 until our input signal got above 2 volts. So I went to Wikipedia and got the definition for a Schmitt trigger. And basically in electronics, when the input is higher than a chosen threshold, the output is high. When the input is below a different lower chosen threshold, the output is low. And when the input is between the two levels, the output retains its value. This dual threshold action is called hysteresis and implies that the Schmitt trigger possesses memory and can act as a bistable multivibrator, latch, or flip-flop. One application of a Schmitt trigger is to increase the noise immunity of a circuit. A Schmitt trigger is a bistable multivibrator and can be used to implement another type of multivibrator, the relaxation oscillator. And you notice this particular schematic that they give you for a relaxation oscillator is identical to the circuit that we're going to be building today. So in part A of our lab, we're going to be using a 74LS14 Schmitt triggered IC, and we're going to be generating time. We generate time by using a big value of a resistor and a large capacitor. The resistor limits the current flow to the capacitor. The capacitor charges up slowly. Once the charge on the capacitor reaches the upper level of the Schmitt trigger, the output will become a logic 0. So looking at our circuit, we can see that the switch is in the closed position going to ground. When it's in the ground position, all the charge is going to come off of the capacitor and go to ground. So right now we have a logic 0 going into an inverter, creating a logic 1 on the output. A logic 1 on the output will turn on our red LED, and because we have a logic 1 on this side of our green LED and 5 volts on the other side of the green LED will not be on. When we open the switch, current will flow through the resistor onto the capacitor plate. Now we're using a large resistor, 100K, so that'll slow down the amount of charge going onto the plate of our capacitor. Our capacitor is 470 microfarads, which is a large capacitor with big plates. So the combination of a large resistor and a capacitor with large plates should create a time delay for us. Eventually, the voltage on the capacitor plates are going to charge to a point where our Schmitt trigger is going to reach its upper level, and it's going to be considered a logic 1, which will give us a logic 0 on the output, causing the green LED to turn on and the red LED to turn off. So the combination of the resistance and the capacitance creates a delayed reaction when we open the switch and go from a logic 0 to a logic 1 on the input. This is my circuit wired up on the trainer. You'll notice I have my 74 LS14. It has power going to pin 14, ground going to pin 7. I have my green LED being powered from the power bus, or plus 5 volts, and the red LED goes to ground through the ground bus. Pin 1 goes through the resistor to plus 5. Notice I picked up plus 5 on pin 14 of the IC. My resistor goes directly to pin 1, which is the input of the first inverter. The capacitor goes directly into pin 1, that would be the long leg, and you can just see the white or the negative side of the capacitor going down to my ground bus. Also on pin 1 I've hooked up a switch, and I'm just using the last switch of my dip switch going to ground. Please notice I've removed the SIP resistor and I've removed the plus 5 volts that went to the SIP resistor. This is very important. When I move my switch to the ground position, I'm inputting a logic 0. It goes through the inverter and shows up as a logic 1, which is the red LED. When I open my switch, the capacitor slowly charges up, and eventually it outputs a logic 0, turning on the green LED representing logic 0. So I have my circuit here, and what I've done is I've connected one channel of my oscilloscope to the connection between the resistor and the capacitor, so I can see the charge on the capacitor. The other oscilloscope lead is connected to my output, so I will be able to see a square wave on there. So I have the oscilloscope set up right now, and I've got the switch in the down position. So this trace right here is the voltage on the capacitor, and you can see it's at 0 volts when the switch is down. And the output of the inverter will be logic 1. So that's the top trace going across the screen. So when I move my switch from the grounded position to the open position, you can see my capacitor starts to charge, and then my output changes. So I'm just going to stop the screen there so you can see I was at logic 1 and then I go down to a logic 0. When my capacitor charges, and you can see that it charges up to 1.4 volts. So when it reaches 1.4 volts, I've reached that threshold for the Schmitt trigger and my output changes. So this is the data sheet for the 74LS14 hex inverter with Schmitt trigger inputs. You can see they give you the connection diagram. So what we're interested in on this data sheet is the recommended operating conditions, and you can see we've got VT+, which is the positive going input threshold voltage, and you can see the minimum is 1.4, nominal 1.6, and the maximum 1.9 volts. So you can see on the output the capacitor was charging, and when it reached that threshold, that 1.4 volt threshold, the output changed from a logic 1 to a logic 0. Once you've wired up your circuit for part A and verified it's working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. In part B of the lab, I'm going to replace the 100k ohm resistor with a 2k ohm resistor. I'm going to eliminate the switch. So when the output of the inverter is a logic 1, that's going to provide plus 5 volts through the 2k onto the 470 microfarad capacitor. As the capacitor charges up and becomes a logic 1, the output's going to become a logic 0, and the capacitor is going to discharge through the output of the inverter. Now I've shown you the output on the oscilloscope, but you do not need to wire your circuit to the oscilloscope. We'll be able to see the output on the LED. So this is my 2k ohm resistor, and it has to go between pin 1 and pin 2. So I'm going to bend one lead over and bring it back down so the two leads are beside each other. I'm now going to trim it so that they're both the same length. So I've trimmed my leads so that they're both the same length. I'm going to put the resistor in pin 1 and pin 2. So this is part B. I have my 470 microfarad capacitor going to pin 1 of my 7414. I have my resistor going between pin 1 and pin 2. I have my output on pin 2 going to the LED. Now I've wired up an oscilloscope here just to show you what it looks like. So I just want to show you what the output looks like on the oscilloscope. You can see that the low time is longer than the high time. So the red light is only on for a brief period of time and it's off for a fairly long period of time. You can see that the capacitor is discharging when the output is 0, and the capacitor is charging when the output is logic 1. I've set up the two cursors so that you can see that it's charging from 720 millivolts up to 1.44 volts. So it's charging between 720 millivolts and 1.44 volts. So looking at the data sheet for the 74LS14, you can see the negative going input threshold 0.4 to 0.8, and we were at 0.7, and the positive going threshold 1.4 to 1.6, and we were at 1.44. Now we're supposed to replace the 470 microfarad capacitor with a 100 microfarad and then a 10 microfarad capacitor, and then redo our calculations. In the lab, I've already done the calculations for you for the 470 microfarad and the 2K ohm resistor. So I'm going to replace the 470 microfarad capacitor with the 100 microfarad capacitor. Remember, the long leg goes to pin 1, the short leg goes to ground. You can see it starts blinking a lot faster. I'm now going to replace the 100 microfarad capacitor with the 10 microfarad capacitor. The long leg goes to pin 1, the short leg goes to ground. You can now see it blinks so fast it's very hard to tell how fast it's going. With the 100 microfarad capacitor in the circuit, the calculation should end up being 4 Hertz. With the 10 microfarad capacitor in the circuit, the calculation should result in 40 Hertz. 40 Hertz means it should blink 40 times per second. So once you've figured out the frequency with the 100 microfarad capacitor is 4 Hertz, and the frequency with the capacitor at 10 microfarads is 40 Hertz, many students ask me, well, what is T? And T is the period of the waveform. So that's from the starting point until the waveform repeats itself. And I've given you the formula, and the formula is T equals 1 divided by the frequency. So 1 over 4 is going to be equal to 1/4, and that comes out to 250 milliseconds. 1 divided by 40 will work out to 25 milliseconds. Once you've wired up your circuit for part B and verified it's working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. Moving on to part C of your lab, we're going to start building Astable multivibrators with the 555 timer. Section 9-7 of your textbook talks about Astable multivibrators, or clocks. And figure 922 of your textbook shows you an Astable multivibrator output, which is the clock signal, versus the Monostable multivibrator, and you can see that you need input to trigger the Monostable multivibrator to generate its output, and it outputs a single pulse. And figure 9-23 in your textbook shows you an example of using a 555 timer wired as an Astable multivibrator that we're going to build in our lab. This is the 555 timer that you have in your parts kit. You'll notice it does have the little smile at one end, so this is pin number 1, and it's pin 1, 2, 3, 4, 5, 6, 7, 8. So this is just a small 8-pin IC. This is another one of my data books from my bookshelf, and this is the linear data book by National Semiconductor. So inside the book we have the data sheet for the 555. This one's made by National Semiconductor, so it's labeled LM555. And what I wanted to show you was the makeup of the 555 timer. This shows you all the internal transistors and resistors that go into making up the innards of the 555 timer. And then at the bottom of the page they give you a little diagram of it's the dual inline package, so these are the 8-pin packages that we're going to be using. As with most data sheets, you get some application information, and here you can see that they've got a small circuit set up for you for a monostable operation. And down at the bottom they talk about Astable operation. So they give you a little circuit on how to wire it up for Astable operation. They provide you with the waveforms that should come from the 555 timer in Astable operation. And you can see that while the output is high, the capacitor is charging. And when the output is low, the capacitor is discharging. And they give you sample calculations for the charge time and the discharge time and the total period. And you can see that they're using a constant of 0.693. I've created a MultiSIM simulation of the 555 timer, and what I've done is I've drawn a rectangle around all the components that make up the 555 timer. The 555 timer is made up of two major components, the first being comparators. So all a comparator says is my positive leg greater than my negative leg? If so, it outputs a logic 1. It can also be thought as, is my negative leg less than my positive leg? And I'll output a logic 1. Because the LM339 is an open collector output, meaning it doesn't provide logic 1, I've had to use two 5K pull-up resistors to +5, so that when we output a logic 1, the line is brought up to 5 volts. The other major component is the RS latch. Now we know from previous labs that the RS latch is negative triggered or needs a logic 0 to trigger. So I've put my output from my comparator through inverters to generate the logic 0 to activate it. It has both a Q and a Q naught. The Q goes to the output. The Q naught goes to a transistor that's connected to a discharge line. In this case, the transistor acts like a switch. So when the Q naught is a logic 1, the transistor is turned on, causing whatever is connected to the discharge line to connect to ground. Now, internal to the 555 timer are three 5K ohm resistors. The three 5K ohm resistors generate two reference points. The first reference point is 5K divided by 15K times your 5 volts, which is 1.67 volts, or 1/3 of your input voltage. The second reference point is 10K divided by 15K, which ends up being 2/3 of your 5 volt input, which works out to 3.33 volts. Now you'll notice line 6 is called threshold, and down here 2 is called trigger. So what happens here is, if the threshold voltage is higher than 3.33 volts, the comparator outputs a logic 1, resetting your RS latch. So that would generate a logic 0 and a logic 1 on the Q naught turning on the transistor. Down here, the trigger input, when it gets below 1.67 volts, it turns on, setting the flip-flop, generating a logic 1, the Q naught being a logic 0, turns off the discharge line. Over here, we have the two resistors and the capacitor that make up our circuit. So the voltage flows through the two 4.7K resistors onto the capacitor, building up charge. So once the charge gets above 3.33 volts, the first comparator turns on, resetting the latch, causing the output to go low. The transistor turns on, and the capacitor discharges through one resistor through the transistor to ground. Once the capacitor gets below 1.67 volts, the second comparator turns on, setting the RS latch, generating a logic 1 on the output, turning off the transistor, and now once again current can flow through the two resistors onto the capacitor. So I'm going to run the simulation. The capacitor starts initially from 0 volts and slowly charges up. We're waiting for it to get above 1.67 volts. So right now the set line is active. And you can see it's outputting 4.98 volts. So once it gets above the 1.67, we'll see that the set line goes to 0, which has just happened now. So it's no longer setting, but it remembers, right? It is a latch, so it is remembering. Now we're waiting for the voltage to get above 3.33 volts. Now when that happens, we're going to get a logic 1 here very briefly, because immediately the discharge line is going to start discharging our capacitor. So you'll notice that once we get to 3.33 volts, it will start discharging. So the capacitor just hit 3.33 volts, and now you can see it's starting to discharge. Once it discharges to 1.67 volts, we'll get a logic 1 here very briefly, because immediately the discharge line is going to stop discharging the capacitor, and it will immediately start charging up again. And now it starts charging up again, and it'll continue to repeat this pattern. I'll include this simulation below the video in the description. It's for MultiSIM 14.1 or above, so that you can run the simulation and see it for yourself. Now on the schematic that I've given you, you can see that pin 5 is your control voltage, and it has to go through a capacitor to ground. A lot of times students will connect this directly to ground, and the 555 will not work. It has to go through a 0.01 microfarad capacitor, and a 0.01 microfarad capacitor is 10 nanofarads or 10,000 picofarads, which would be a 103. Also notice that pin 6 connects to pin 2, so the threshold and trigger connect together. So this is my 555 timer IC, and you can see that I've got the little smile down this end of the IC. So this is pin 1 that goes to ground, and you can see over here is pin 8 that has to go to power. I also said the pin 4, which is your reset line, has to go to power because you don't want it reset all the time. This is pin 5, and it goes through this little tiny capacitor to ground. Pin 2 is connected to pin 6, so that's this white wire right here. Pin 6 goes through a 4.7 k ohm resistor that I have standing upright to save space on my board, and it goes to pin 7. And pin 7 goes through a 4.7 k resistor to plus 5 volts. My output is on pin 3, going to my 2 LEDs. My last component to go in is the 100 microfarad capacitor, and remember the long leg goes to pin 2, the short leg goes to ground. Now when I power up my circuit, you can see that the lights blink back and forth between logic 1 and logic 0. Red is logic 1, green is logic 0. You can see I've done the example calculations for this circuit, and the frequency it should operate is at approximately 1 Hertz. So you can see on the output, the red LED comes on every second. I just wanted to show you the output of part C on the oscilloscope, and we said note that the red LED is on longer than the green LED, so it's at logic 1 longer, and when you look up here you can see that it is at logic 1 longer, and it's at logic 0 shorter. We can see that the capacitor is charging and discharging, and it's charging between 1.52 volts and 3.04 volts, and it should be charging between 1/3 and 2/3 of VCC, which is 5 volts, so it should be charging between 1.6 and 3.3 volts, and we can see that it's pretty close here. Now here I wanted to show you that we're starting the waveform when it goes high, and we end the waveform when it's completed its low cycle. So from here to here would be one complete cycle, or the complete period, and we can see that the period here is approximately 1 second, and it works out to 970 millihertz. And our calculations show that the period should be somewhere around 977 milliseconds, and the frequency should be around 1 Hertz. So we're pretty close to what we calculated. Remember, there's a 5% tolerance on the resistors and approximately a 10% or better tolerance on the capacitors. Once you've wired up your circuit for part C and verified it's working, demonstrate it to your instructor so they can initial it to indicate that it is complete. For part D, what we're going to do is we're going to add a diode to the circuit. This is just a standard 1N4001 diode. It's black with a silver band on it. And what this is going to do is it's going to allow current to come in through the 4.7K resistor, through the diode, and charge up the capacitor. Then when the discharge line becomes active, the capacitor is going to discharge through the 4.7K through the discharge line to ground. What this is going to allow to happen is we're going to get approximately the same time to charge and the same time to discharge, so we should end up with a 50% duty cycle. So this is the circuit of part C, and what we're going to do is modify it for part D. So I'm going to now put in my diode, and the diode goes from pin 7 to pin 2, and pin 2 is going to have the little bar on the diode facing pin 2. And now you can see that the red and green LED are both on or off for the same amount of time. This is the circuit without the diode, and you can see that the red LED is on slightly longer than the green LED. When I place the diode in the circuit, you can see that the red and green LED are both on for the same amount of time. The output for part D, shown on the oscilloscope, shows that the high time and the low time are a lot closer. We can still see the capacitor charging during the high output and discharging for the low output. It's still charging and discharging between 1.5 and about 3.04 volts. And when I measure the period from the time high to the time low, and it repeats itself, I can see that the period is 800 milliseconds, equating to 1.25 hertz. And when I look at my example calculations, you can see that the period was supposed to be somewhere around 650 milliseconds, and it turns out ours is closer to 800 milliseconds. And the frequency was supposed to be 1.5 hertz, and we're at 1.25 hertz on the oscilloscope. So in part D, what we're trying to do is have the capacitor charge through one resistor and bypass the other resistor with the diode. And then when it discharges, it just discharges through one resistor to the discharge line. Unfortunately, the diode is going to take up a little bit of the voltage drop, so it's not going to be exactly 50%. It's going to take just a little bit longer to charge up our capacitor than it is to discharge our capacitor. And when you look at the output on the oscilloscope, you can see that it does take a little bit longer to charge than it does to discharge due to the current having to flow through that diode. The exact length of the high time is 450 milliseconds, and in our calculations we calculated 325 milliseconds. For the low time, we have 350 milliseconds, and in our example calculations we calculated 325 milliseconds. So when using a diode, we get very close to a 50% duty cycle, but not exact. Now in part D of the lab, we want you to remove RA, which is the 4.7K resistor. So that's this resistor right here. So this is RA, and I've replaced it with a 100K ohm resistor, which is brown, black, yellow. You can see that the red light is on a lot longer than the green light. So I've shown you the example calculations when RA and RB are both 4.7K ohm resistors. Now you've replaced RA with 100K ohms. I need you to fill in the calculations down here. I've replaced RA with the 4.7K ohm resistor, and RB is now the 100K ohm resistor. And you can see that the green light is now on a lot longer than the red light, indicating it stays at logic 0 a lot longer. I now need you to fill in the table for the case where RA is 4.7K ohms and RB is 100K ohms. Remember, when RA was 100K, the red light was on a lot longer than the green light. So it was logic 1 a lot longer than 50% duty cycle. When RB is 100K, the green light was on a lot longer than the red light. So the duty cycle will be a lot less than 50%. Once you've wired up your circuit for part D and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. Part E of the lab uses the 555 timer as a monostable multivibrator or a one-shot. You can see I've given you an example calculation here, and the pulse is going to be approximately 1.1 second. Section 9.8 of your textbook talks about monostable multivibrators, and figure 9-26 is the circuit that we're going to be wiring up in part E. I've given you very specific instructions in the procedure. To trigger the one shot, the switch has to be closed and then open before the one shot is finished, or else it'll continue to re-trigger your one shot. This is the completed circuit for part E of the lab. You can see that I have my 555 timer. I have pin 6 and 7 jumpered together. I have pin 7 going through a 10 k ohm resistor to +5, and I have my 100 microfarad capacitor going from pin 6 to ground. It's very important that when you trigger your one shot that you do it from a logic 1 to a logic 0 back to a logic 1 very quickly. The output pulse is going to change for approximately 1.1 second. If you keep the switch in the down position, the output pulse will stay high all the time that the switch is in the down position, and then when you move the switch to the up position, it will change back to logic 0. This is not a correct one shot. We need to go down and up quickly before the pulse times out. I'm going to show you the output on the oscilloscope, but you do not need to wire your circuit to the oscilloscope. So this is the output of the one shot. You can see here on the bottom trace, this is my trigger, and on the top trace, this is my pulsed output. You can see that it covers just a little more than 2 divisions, and at 500 milliseconds per division, it's just a little over 1 second. It's very important that you get this trigger pulse back up to logic 1 before the one shot times out. So now I'm going to show you what happens if you don't get the switch back before the pulse completes. You'll notice if you don't bring the switch back in time, it's going to extend your pulse width. Once you've wired up your circuit for part E of the lab and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. In part F of the lab, we're going to be using a monostable multivibrator, the 74221. And I want you to notice in the calculation, we've changed from a constant of 1.1 to a constant of 0.7. I want you to notice that on our lab we're going to be using the 74221 one shot. Your textbook uses a 74121 one shot, but this part has become obsolete. I want you to notice on the pinout for the 74221 that there are actually 2 one shots in this package. The one that's in the textbook only has one shot in the package. Figure 9-27 of your textbook shows an example of a one shot using a 74121. We're going to be using the 221, which is wired up identically. And I want you to notice that the positive end of the 100 microfarad capacitor goes to pin 14. The negative leg goes to pin 15. So this is the circuit for part F of the lab. And I want you to notice that I've removed the SIP resistor and put in the 100k ohm resistor that they'd asked for. This little blue wire comes from the switch to my 103 capacitor. Remember, 103 is 0.01 microfarads, and that goes to pin 1. Notice that pin 2 and pin 3 go to power, pin 8 goes to ground, and pin 16 goes to power. Pin 15 goes through a 10k ohm resistor to +5, and the capacitor goes between pin 14 and 15. And remember that pin 14 is the positive end, or the longer lead, and pin 15 is the shorter lead. Pin 13 is the Q output, and that'll go to the red LED. And pin 4 is the Q not output, and that'll go to the green LED. When I trigger this one shot, it should go for approximately 0.7 seconds. To trigger it, all you have to do is move the switch from the up position to the down position. I just wanted to show you the output of the 74221 on the oscilloscope. You can see the bottom trace here is my trigger, and the top trace is my output pulse from the one shot. You can see I've got my division set up as 500 milliseconds per division, so we're getting an output pulse of approximately somewhere around 700 milliseconds. If I set up my cursors on either side of the output pulse, you can see I'm getting 706, and our calculations show us we should get somewhere around 0.7 or 700 milliseconds, so we are quite close. I also want to show you that if we extend the trigger pulse, so you can see I've extended it past the output pulse width, and you can see that the output pulse does its 700 milliseconds and then resets before it waits for the next trigger to come along. To re-trigger the one shot, move the switch back up to the 1 position and then move it down to the 0 position. Sometimes the one shot will not trigger, so you can take a piece of wire and put it into ground and then just touch pin 1 to trigger it. Now the last question asked, does retriggering the one shot extend the high time, yes or no? So let's just keep touching and see if that extends the high time. And you can see that it does its one shot, but it doesn't extend the high time. It has to finish doing the one shot before it can come back and retrigger again. So this is considered a non-retriggerable one shot. So I've given it multiple pulses, and you can see that it does have to do its 700 milliseconds before the next pulse triggers the next output, and you can see that it actually has to time out the 700 milliseconds before it does get the next pulse. So this pulse here, to trigger it, is being totally ignored until the output cycle is completed. Notice there is a second part to part F. We're going to keep R2 at 10K, and we're going to change our capacitor to 470 microfarads. Changing the capacitor to a larger capacitor should extend our pulse width beyond 0.7 seconds. Please do the calculation here. I just wanted to show you that if you do look up the data sheet for the 74LS221, it is called a dual non-retriggerable one-shot. Once you've wired up your circuit for part F of the lab and verified that it is working, demonstrate it to your instructor so that they can initial it to indicate that it is complete. On the last page of the lab, we have 10 questions for you to answer and hand in. If you are looking for answers, open your textbook. Page 1 of the lab shows some hints, and in this case it's solve problems 9.42 to 9.58 and 13.60 to 13.63.